is about the mechanical restraints toolbar that is available in the generative structure analysis. Now, most probably, well, there's a lot of video segments in this channel, and in those, the ones that deal with finite elements, I have never used the mechanical restraints toolbar except for extensive use of this first one, which is called surface slider. So what I would like to do is through examples show you what these other ones are, and these are the ones that are slider, pivot slider, I believe spherical joint or ball joint, and a pivot. Okay, although the documentation in Catia is not too bad, but it is difficult to read it and decide what exactly is it that they're getting at. So, but still better than some other segments of the documentation. Okay, so let's go ahead and deal with a problem that is useful in explaining these toolbars. I have created a plate here, a solid object here, and dimensions and things like that are irrelevant, but I applied material property on it. Now we're going to go and mesh it in generative structure analysis. Okay, just so that things are not too ugly, let me go ahead and change the size here to point maybe 2. Let's see how it looks like. Okay, so it looks like that. So if you mesh, it will be relatively fine mesh. Okay, so let's deactivate this. The other thing is that, as you are aware of, when I use parabolic elements, the displacements don't always come out right as far as the shaded contour because of my graphics card. All right, so let's move on. Now, what I would like to do is consider several cases where each one of these restraints are discussed. Now, first of all, here is the restraints toolbar, and obviously, I think you're familiar with a clamp, and you're familiar with user-defined restraint. So we're looking at this sub toolbar, which is called mechanical restraints, right there. Okay, mechanical restraints. Now, if you're using any of these four, for example, this is called slider, this is called sliding pivot, ball joint, and pivot, except for the first one. If you're using any of these four, you need to create a virtual part. Now, the discussion about virtual part, rigid virtual part, and smooth virtual part was already carried out in an earlier presentation, so we're just going to stick to the virtual part, rigid virtual part, and forget about the smooth virtual part. So, what I need to do is I'm going to create a virtual part with this support. And remember, if you don't choose a handler point, the handler point is actually placed at the centroid of the support. And then I do another one on this side, another rigid virtual part on this side. Again, the handler point is placed at the centroid. Very good. Now, let's do the following. Why don't we make these two rigid virtual parts apply pivot on them? See that pivot? The fifth one on the right, pivot. So we're going to put a pivot on this end. Now, what this thing means is that it's as if there was a hinge here. This pivot means there is a hinge here, that this can actually rotate about that hinge being right now along the axis of the cylinder. It can rotate about that. It cannot translate, and when it says pivot, it can also, it cannot translate at all. Okay, Now, how do you decide, for example, what the direction of this pivot is? That's done through here. For example, if you say, let's hypothetically say you say x equal to 1. Notice what happens is that this is x equal to 1. In other words, the axis of the pivot, the hinge, is along the x direction. On the other hand, if I make it 1 about y, look at what happens. So the axis of the hinge is along the y direction. If I want, for example, z vertical, the axis is like that. In other words, this can pivot or hinge about that axis, but it cannot go up and down. It cannot translate at all. You know, the translation is restrained. Okay. Now you can also have an arbitrary orientation, for example, something like that, which obviously that's not what we want. Okay. So let's start with axis along x, which is right there. And let's also do another one on this side. Another pivot. This is pivot to that virtual part. Same direction. Okay, good. We're now going to apply a pressure on the top face. Okay. So we say, all right, and let's run it. Okay. So look at the deformation. Notice what happened is that if you look at the view from the front, which I believe is this, okay. So notice that what happened is that it's as if I have a hinge here that this plate can rotate about it. But if you look at it from the top, the view from the top, same thing by the way on this side, you can see that. This was the original configuration, and it's rotated about it. If you look at the view from the top, which is right here, right, okay. This length, let's see if this length changes. Just 1 second. Let me activate the actual part here. Here's the actual part. Okay, let us magnify the size here. So make it 100 times. Okay, notice that these ends are completely restrained from shrinking or expanding. Okay. Okay. So in fact, if you look at the view from the not this side, look at the view from that side, and you animate this, the original size and the final size, which is this blue one, is the same on that support. So hinge allows it to rotate about this, bend about that, but these ends are completely fixed. All right. So, okay, let's make a change here. Let me take one of these. So let me see for a second. Okay. Let me deactivate first of all this deformation. We're going to experiment with a bunch of cases that we're going to run to see perhaps whether we can understand what's going on. Okay, now this one, I'm going to change it to slider. Slider is right here. This was pivot. This is slider. Okay. Delete it. And this time you make it a slider. Slider means it cannot rotate, but it can translate. Okay, so the direction of it is correct. So in fact, but if I want to, I'll make a 1 here along X. It doesn't change. Look at the, by the way, the shape of this thing. That means it will not allow it to rotate about this. Very similar to the clamped beam, that the angle of rotation is 0. But it can slide. Okay, so let's run it. Let's look at the deformation. You see what happened? If you look at the view from the front, you see this end was supposed to rotate because it was a pivot. This end is not allowed to rotate. It's vertical. And if you look at the side view, for example, let's look at this. No, side view. Let's look at that. The length of this thing can actually change. So let me, okay, let's look at the actual part. Here's the actual part. Right there, you see that? It has been allowed to slide. In fact, if I make the scale bigger, maybe 300, you see, it can actually slide, but it cannot rotate. Okay, you can see that. See, with a pivot, this could not have happened. All right, let's try another one. Let's look at the isometric view. Okay, deactivate this plot, and this slide, I'm going to delete it and replace it with sliding pivot. Sliding pivot. Now, sliding pivot means it allows you to rotate. It allows you to rotate, and it allows you to slide. Now, in this particular problem, you may not see the sliding effect because there's nothing which actually causes that sliding. Everything is symmetric. The load is from the top. But let's run it to see what happens. So this particular load may not reveal what happens here. So let's actually deactivate that. Activate that. Okay. And I made it scale too big, so let's make it 200, more civilized. Okay, and let's bring the part into the picture. Okay, and look at the view from the side, which was, I believe, this. Okay, and you see, even here you can't see any sliding because there's nothing that actually makes it slide in that direction. Okay, but when I change my loading direction, you will actually see what happens to that sliding pivot. So let's go back here. Okay, deactivate this. Deactivate that. This time take the load here, this load that I applied, and instead of the top, let's apply it on the side. Okay, so we have a pivot here, which means it will not be allowed to slide. It will be around to rotate. Here is a sliding pivot. See that? Sliding pivot. Okay, right there, you can see that. Sliding pivot. And the load is on the side. Okay, so let's run it. This side will rotate and will actually slide in the X direction. See that? Good. Now let's make actually this back to, let's put it back to, in this particular loading, let us put it back to a pivot, which means it will not be allowed to slide, and see what happens. So I'm going to delete this. I'm going to put a pivot here, right there, and run it. and you will see that there will be no sliding this direction. The load is on the side. You can see that, not on the top, on the side, right there in this direction. Let's look at it. There. If you look at this thing from the top, this is what you see. Notice that it is actually bowing out in this direction, but at the ends it will not be sliding because pivot restrains. If you look at the icon here, there are these planes here, which means that there will be no motion in this direction, whereas for the pivot there is a motion in that direction. This is a slider. Remember the one with the square cross section? It also allows to move in this direction. Okay, now let me deactivate this. Let's take the same problem and make both of them sliding pivot and see what happens. So where is this? Let's put the view isometric. Deactivate this. Delete this. And delete the other side. And turn them into either slide or sliding pivot. Slider or sliding pivot. Delete. The effect is the same. So let me actually convince you that with one of them, I'm telling you that with the slider or pivot, sliding pivot, you're going to run into a problem. You see that. So let me use a sliding pivot. There in the X, fine. What is this? This is a slider. Actually, I use a slider. That's okay. And I use a slider here on this side. You get exactly the same effect if you use sliding pivot. I'm not going to do both of them. We're going to try to run this. And of course, it will bomb out. Because there is no training, there is no restraining force in this direction. Just look, it'll fly away. It just moves as a rigid body. You can see that. The same thing is going to happen if you use, instead of a slider, sliding pivot. Now, let's do the following. Let's try the same problem here. I will take deactivate that. The one that I have not used is this ball joint. So let's take one of these sliders. This one I deleted. The other side I'll keep. Remember, and now I'm going to put a ball joint here. A ball joint. Ball joint means that this will be allowed to, you know, cannot translate, but it can rotate definitely in any direction. Let's run it. This will of course run, but I will change the load to show you. Perhaps this may not be very revealing what exactly is going on. Okay, it did work. Let's look at the deformation and change the scale so that it's like this. Let me make it, I don't know, maybe 100 so you can see it better. There. Notice what happened is that because this was a ball joint, this cannot fly away. It can rotate and everything, but in this direction, this is a slider. This was a slider, or the same thing could have happened if this was a sliding pivot. We can see that it's just moving. Now, what I'm going to do is the following. I will take the load and put it in a different direction, perhaps for you to see what's happening in a more revealing way. So let me delete this. Let me delete this pressure, and instead put a force, upward force on this edge. So where is the force? Right here, in the upward direction, which is Z. I'll put 100. Take this thing out. So we have a force upward. It's going to run. You'll see. And look at the deformation. There. Let's change the scale so that we can see it better. Perhaps 1,000. There, you can see. Because this is a ball joint, it can actually, rotate in this direction also. And the other side is a slider, which prevents it from sliding, and it keeps the angle also at 0 degrees, prevent rotation. All right, I hope that this sheds some light on this mechanical restraints toolbar. I don't use it very often because some of the stuff that you want to do can be done with extra additional work using user-defined restraints and perhaps slider surface and this. So, but this is useful in many situations, and